What I'm going to talk about today, my title is From Superconductors to Giant Planets, a Computational Window of Materials. And so I kind of thought of a jazzy title to encourage people to come and have a listen. But the main focus of the talk is going to be the computational tools that we use to make the various discoveries that we've made, which indeed range from superconductors to giant planets. So the technique that I'm going to talk about is structure prediction, and it's a technique that essentially answers the basic question of what structure will a collection of atoms adopt. And this seems a fundamental scientific question, but it's striking that around the time when I started working in materials modeling or electronic structure theory, that was just not the way things were done. If you were doing an electronic structure calculation, typically your structures would be relatively simple, maybe a simple primitive cell of a well-known semiconductor. And certainly those structures will have been derived from experiment, or in some cases hypothetically built by hand. My subsequent work, my postdoc years worked, and my PhD years worked in the development of theoretical spectroscopy techniques. And really, from my point of view, those techniques hit a brick wall when it came to their usefulness from a scientific point of view, because obviously we developed the quantum mechanical techniques that allowed you to predict a spectral signature from a given crystal structure. But if the crystal structures that we were offering the software had already been derived from experiment, there was little need really to do those simulations. We already knew what the structure was. The analytical point of spectroscopy was not being fully utilized. So it felt to me that we needed to have a way of generating candidate structures that we could then match and compare with experiment. And it turned out, of course, techniques existed for this in the field of materials modeling, but they largely used empirical models for the interactions between the atoms. And as such, the description of the energy landscape, which is fundamental to structure prediction, was not well described. So it might well describe the energy landscape of around a few chosen local minima or low energy structures. But if you wanted to explore the whole energy landscape, there'd be regions where the potential had not been parameterized or fit. So it seemed to me, and especially given that I was a developer of the CASTEP code at the time, that the obvious thing to try was to try and do this, from first principles. Now, the challenge was that running density functional theory calculations 20 years ago was relatively computationally expensive. We were helped by the fact that the multi-core chips or multi-core chip architectures had come along. So we were starting to get wide access to parallel architectures for the whole scientific community, rather than just those that had access to large supercomputers. So it was just really at the stage where you could just think of doing large numbers of DFT calculations and start to use these first principles methods to explore the energy landscape. Now, I want to be clear here. I say structure prediction. Often it's shortened to CSP for crystal structure prediction. But actually, in my mind, I'm as interested in non-crystalline structures as well. That might be point defects or interfaces, grain boundaries in materials. As I'm now in a materials science department, it's very much drummed into me and our students that real materials are complex and full of defects. That apparently is what makes them interesting. But in this field, for simplicity, a lot of the early work was done in crystal structure prediction, where we could maximally exploit periodic boundary conditions and translational symmetry. So the method that I tried in those early days is actually exactly the same as I use today, and it may seem surprising that that's the case. So the first thing I tried was to randomly sample the initial configurations of a putative crystal structure, apply local optimization using density functional theory, so moving the atoms using forces and the shapes of the unit cell using stresses, and at that time doing it 10 or 20 times to try and pick up a representative sample of the low energy configurations. Now, I think it's completely reasonable that that's the first thing you would try. I would be surprised if anyone tried anything more sophisticated to start with, but a little extra thought is required to understand why maybe that's actually a good thing to do good thing to do, full stop. So the key thing that makes this algorithm or this approach work is the ability to do many calculations at once. And as over these last 2 decades, the availability of computational resources have grown quite dramatically, to the point where I think it's relatively common for a researcher to have access to something like 1,000 compute cores on which to do their searches. So when I started doing random structure searching, I started with I don't know, 2 cores or 4 compute cores. Whereas now in my everyday work, just to give you a scale of the computation involved, I will tend to be running 1,000 cores at once, each individually doing their own structural optimization. So the ability to do large numbers of calculations was key, but maybe we should think a little bit about why is random structure searching still a good thing to do. There are competing approaches for structure prediction, particularly those involving some sort of learning from experience from previous calculations, such as evolutionary or genetic algorithms, or very well-known particle swarm algorithms. So why does random structure searching still hang around? Well, the way I look at it, there really is no single correct answer for doing a global optimization or search on an arbitrary energy landscape. This is some form of the no free lunch theorem, but you can choose different approaches for different situations. So in my line of work, I'm most interested in discovering new things. That's what makes it interesting for me to run these calculations, and I hope it would the users of AIRS as well find some of that excitement. So for me, it's not so important absolutely how fast I can find a known structure. So I wouldn't want to benchmark against how quickly can I rediscover diamond. It's much more interesting to reliably find new things. And so this is part of the exploration or exploit versus exploitation dilemma. So a learning type algorithm is aiming to be efficient. It's aiming to extract as much information from previous calculations to accelerate future searches. Whereas an AIRS, a random sampling strategy, doesn't do any exploitation at all, but it really focuses on exploration. It's looking every time a new structure is generated. If you're trying to choose from a uniform distribution, not a distribution with a Gaussian distribution around any particular parameters, it's very important that we sample from a uniform distribution. And so each new structure you choose has a chance of finding something radically new. Now, towards the end of the talk, I'll explain a little bit about how we're bringing some exploitation into AIRS, into random structure searching, but it's done in a very explicit way. So we still use exactly the same sampling-based approach, stochastic sampling-based approach, but at certain stages we introduce some exploitation of previous results. So another reason why random structure searching hasn't gone away is because it works very well with the increasingly parallel computers that we have. It's known as a trivially parallel algorithm. Each individual random sample or random structure that you optimize is done separately from all of the others. So if you wanted a pathway to exascale computing, random structure searching is an approach that can fully exploit the entire computational resources that you have. There's no or very little communication behind each individual run. Now, in addition to that, each individual random sample is uncorrelated with all the other samples. A learning algorithm, each new structure you generate, if you're going to be exploiting previous information, will be correlated to what's gone before. But because there's no learning at all in a random search, they're uncorrelated. And this actually has some nice features. It allows you to have confidence in your research. So I'm often asked by people who are learning to use random structure searching, they ask me when they should stop their search. And that's actually a really good question. And there is no simple answer to that. When you're doing your search, because it's a stochastic algorithm, there's no natural stopping point. But because the runs are uncorrelated, there becomes a natural non-stopping point. So, for example, if you're searching for a new in a new compositional space, and you've discovered a new structure, and you're very excited, and you think that this structure is the one that's going to allow you to write your next PRL paper, I can tell you when not to stop. Do not stop until you have found that structure multiple times. In many, and what this is doing is this is telling you that you're starting to fill the energy landscape, or the basins in the energy landscape. You're multiply sampling the low-lying wells in the energy landscape. So this gives you a non-stopping point. Many times in my use of random structure searching, I've discovered even better structures when I've forgotten to stop a calculation before I go away for a weekend. So there really is no final answer here. It's one of the sort of nice things about the field. As people try harder and search more, there's always the chance of something else coming up in these searches. Particularly as algorithms get faster, we start to explore larger and more complex unit cells. So the other feature I think that's quite strong about random structure searching is that it's incredibly straightforward. The number of parameters that you need to explain or communicate to a reader or someone that you're training is very, very minimal, and they're easy to communicate. So when you're doing a random structure search, of course, you have to choose roughly the right volume or density of your system. You might put some distance constraints so atoms don't fall on top of each other. You might exploit symmetry or structural units. But these are all terms that scientists in general talk about. These aren't abstract parameters of exotic algorithms that are based on animal behavior. These are the terms from physical science and solid state chemistry. So this helps a lot in the communication of the algorithms. So I'm just going to show a couple of examples of what a random search looks like. What does an initial random structure look like? Well, it looks something like this. So what we've got is 28 atoms of boron in a fixed box. They're randomly distributed in that unit cell. You can see that they're periodically repeated through space because it's going to be a crystal. And I've made sure that the atoms don't sit on top of each other. So there's an exclusion distance around each of those atoms. And so this might be an initial random structure, and then you feed that into a code like CASTEP, your favorite DFT code, and tell it to relax, and that structure moves downhill until it can't go downhill anymore, and then you're stuck in a local minima. And you can see that this final structure doesn't look much less random than the initial structure. What we found is something like an amorphous form of boron. Now, this is what in a large unit cell, this is what you'll often find. But in this case, 1 in 100 times, if you start from this random structure, for example, or others seemingly different, but with the same end point, you get an optimization that looks like this. So it looked completely random to start with, but it was just in the right initial random conditions that when it relaxed, the atoms clicked into these beautiful structures. This is the very famous gamma boron phase with its famous icosahedra of borons and dumbbells of borons, and there's charge transfer between these different units. Very beautiful crystal structure. Okay, so this method was developed by myself during my postdoc years, and I was at that time mostly interested in carbon phases. Now we'll come back to carbon later on, but I was very lucky to have a colleague in the Cavendish laboratories, Professor Richard Needs, who was interested in high pressure physics. In fact, he was interested in high pressure hydrogen. And at some point, he observed me discovering these novel carbon structures using random sampling, was a bit surprised at what I was up to, and then asked me whether I could do the same for hydrogen. And he explained to me that the opportunities and challenges in high pressure physics, and following that, we had a very successful collaboration exploring many possibilities under high pressure. So when you're doing high pressure calculations, compared to the challenges of the experiments, which are shown at the bottom, ranging from a large anvil press to a diamond anvil cell to the National Ignition Facility in Lawrence Livermore, or even atomic explosions to generate extremely high pressures. From a computational point of view, all we have to do is, instead of minimizing the internal energy U, we minimize the enthalpy, which is U plus the pressure times the volume. And I think of this as a penalty function against volume. So this is an optimization which is penalizing structures with high volume, and the degree of penalty is determined by this pressure pre. P. Now, why is high pressure interesting? Well, it's interesting. It's a frontier in its own right. You could always ask the question, what happens if you squeeze materials harder? But it's also relevant to our understanding of the natural world, in that much of the matter in the universe gathers together or clumps together under the action of gravity. And deep down in those astrophysical objects, the pressures encountered can be very large, ranging from the tens of gigapascals of the moons of Saturn or Jupiter to the 100 gigapascals or megabar pressures in the center of the Earth, more like 300 gigapascals, to the tens of terapascals in the center of Jupiter, and all the way to petapascals in stellar objects or encountered in nuclear-style explosions. So the exploration of high-pressure materials turned out to be a golden opportunity for structure search. And it was a golden opportunity because exciting things were expected to happen, but the experiments were really, really difficult. And so, relatively speaking, we had an open field in the early days of structure prediction. Not just myself, also Artem Oganov and Yangming Ma with their respective projects. Together, we were able to explore a wide range of materials behavior at these very high pressures, and often discover things that had not been anticipated experimentally before, but often confirmed by experiments not that long afterwards. So in my case, the first application of random structure searching was to studying a suggestion by Neil Ashcroft that silicon H4 or silane might become superconducting at high pressures. And in fact, that's the paper where the Ayres algorithm, or the random structure searching algorithm, is first introduced in a short paragraph that it explains how you can discover crystal structures from first principles. But following that, we went on to explore the high pressure phases of hydrogen. And in fact, most of the theoretical candidate structures for hydrogen under pressure have been derived by Ayres style calculations. And indeed, some of our phases are now the best models that experimentalists have for hydrogen at high pressure, in particular phase 3 and various forms of phase 4. We also went on to explore the behavior of the hydrogen-oxygen system at high pressure, and found that at very high pressures, the H2O composition was not stable. And then looking at aluminium, which is a sort of well-known simple metal at lowest pressures, we discovered that there was quite a dramatic phase transition from these simple structures to a complex host-guest, incommensurate, sort of like a one-dimensional quasi-crystal structure at terapascal pressures. And in fact, that result stimulated a lot of interest about the possible richness of behavior of materials at high pressures, at the kind of pressures that experiments like the National Ignition Facility might explore. Now, I'm just going to turn back to Neil Ashcroft's suggestion that hydrogen mixed with other elements might become high-temperature superconductors, because this has actually spawned a whole very active field of research whose conclusion has not yet been fully worked to the end. So what Neil Ashcroft proposed in the early days, in the 60s, was that potentially metallic hydrogen might be a high-temperature superconductor. And that was based on a simple model of superconductivity, which related the superconducting transition temperature to the Debye temperature, and then some electron-phonon coupling terms and density of states terms of the electronic structure in an exponential. But the key thing from here was that if you want a high TC, you're going to want to have a high Debye temperature. And so Neil Ashcroft suggested that hydrogen could give you access to that, because the frequencies of vibration of hydrogen, because of the lightness of the hydrogen, could be very high. But it turned out to be difficult to find metallic hydrogen. So later on, Neil Ashcroft suggested, both in 2004 and a bit later with a concrete suggestion in 2006, that maybe we could achieve this effectively metallic hydrogen, but through forming a compound or some chemical pre-compression with other elements. And his concrete suggestion with Roel Hoffman was that silane might be a good place to start. By hand, and various other methods, they constructed some candidate structures. They computed the electronic structure and then suggested from the electronic structure that they might be high-temperature superconductors. Now, this was the point that we started with our random structure searching. We saw this result and we thought, well, could that be true? Because it looks like they built the structures by hand. why not try an unbiased approach to do this through structure search? And very rapidly, using this random structure searching, we found much more stable structures than those that they had suggested. And at the pressures where they felt they had superconductors, we found that a band gap actually opened up. It was not a metal and therefore couldn't be a superconductor. But at higher pressure still, the material did appear to become metallic. So we left open the possibility that maybe silane at high enough pressure might become a superconductor. So that was the start of our foray into that field. And the basic reason we're able to do these, even think about designing superconductors from first principles now, is because of the existence of a set of experimental and, in particular, theoretical and computational techniques for conventional superconductivity. So I'm going to leave unconventional superconductivity and the cuprates to one side for the time being, but to point out that with techniques like random structure searching and other structure prediction techniques, we can explore theoretically the range of possible structures that might exist. And with a parallel development, which was not that I can take no credit for, but particularly built around the quantum espresso computer code, it's become possible that from a given structure to compute the superconducting transition temperature using various approximate methods, but largely involving computing phonons and electron-phonon coupling constants. So combined with the ability to do high pressure synthesis and analysis of these materials, with these three branches, we can imagine now going around a loop between theory and experiment and hunt for superconductors. So this is the state of the art, I guess, in the end of the around 2019. It's a review article I wrote with Ion Eria and Mikhail Eremets in the annual reviews of condensed matter physics, where we highlighted the experimental confirmation, really, of lanthanum hydride and hydrogen sulfide as the new kids on the block in the field of high pressure, high temperature superconductors. Now, in both the cases of hydrogen sulfide and lanthanum hydride, there had been theoretical predictions that these would be good materials to look at, and indeed the experimentalists involved were very much driven by those theoretical suggestions. And there was right from the very beginning there was a clear synthesis between experiment and theory. Now, of course, this is very tempting. We've got a curve that's a line that's rising very steeply with time, and it tempts us to think that there may be the possibility of finding room temperature superconductors, and there's a wide effort across the globe of people using structure prediction techniques and prediction of superconducting transition temperatures to try and see whether we can reach this limit. So what I'm showing here is some of our efforts. So there are many others in the across the field, but this was work that I did with Michael Hutchian and Alice Shipley, where we did a high throughput prediction of structures across the whole periodic table for binary hydride superconductors at a range of different pressures. And each of these red dots on the plot here is a computed superconducting transition temperature for a relatively stable, certainly dynamically stable crystal structure that we found in our high throughput searches. Often we rediscovered structures that had been proposed before, but many of them were new. Now, the most striking thing for me about this result was that as we lowered the pressure, the maximum superconducting temperature that we found was certainly decreasing a bit, but it wasn't decreasing very rapidly. So this suggested to me, and probably to others as well, that it really might be worth looking at lower pressures down to ambient conditions to see whether there are any potential or candidate structures that might be superconducting in this range above 50 GPa or 50 Kelvin or so, which would then surpass magnesium diboride as the highest TC conventional superconductors. So this is the result of some work that we've done in that direction very recently. It's been posted on arXiv just a few weeks ago. It's been in collaboration with my postdoc in Cambridge, Kapildeb Deluy, and others, where we have repeated that high throughput random structure search for a wide range of, in this case, ternary phases rather than binary hydride phases at ambient conditions. We are only now interested, actually, in superconductors at 0 GPa. And so what we do is very extensive searches across wide ranges of compositions to pick out stable or close to stable phases, and then compute for as many as possible the superconducting transition temperature. Now, to make life easier for ourselves, we constrain the structures to be relatively simple without too many atoms in the unit cell and to exhibit fairly high symmetry. So this is based on the observation, at least so far, that most of the high TC conventional superconductors have exhibited high symmetry. So we use that. That makes the calculations very much more efficient, but it also simplifies our search. So what I'm showing here is the result of this search. So obviously we found very large numbers of candidate structures. And what I'm showing you is the best one. The best structure that we came up with was magnesium to iridium H6 in a cubic phase, which is metastable at elevated pressures, but potentially offers a route to synthesis via very closely related stable phases. So there's a very closely related Mg2 IRH7 cubic phase that if we could encourage it to lose a single hydrogen, it would become metallic, and we predict a high temperature superconductor, which, with according to our calculations, at ambient pressures to have TCs in excess of 160 Kelvin. Now, these calculations are extremely sensitive. It turns out that when you do an optimizing search for superconductors, you optimize for materials that are just very perfectly aligned to have maximal properties. And in this case, it's got a very high and peaky density of states near the Fermi surface, which means the calculations are rather difficult to converge in terms of K-point grids and so on. This gives some of the challenge of coming up with a definitive TC. But we are hopeful that these structures are close enough to stable, to being thermodynamically stable, that there may well be, by using pressure and temperature and other techniques, a route to promote the synthesis of this proposed phase. Okay, so that was superconductivity. Now I'm going to talk to you about astrophysical bodies through carbon. Now, carbon's a very iconic element, given it a very wide range of bonding that can be that it can take up. There are the known thermodynamic phases of diamond. Thermodynamically stable phases of carbon are graphite, which is the most stable phase under ambient conditions, and diamond, which becomes stable under elevated pressures. But there are other possible phases of carbon, for example, fullerenes, buckyballs, graphene, nanotubes, and other stackings of diamonds, such as the Lonsdale-like, which is hexagonal diamond. And each of these metastable phases of carbon elicit great excitement and sometimes Nobel prizes. So we noticed that often over the years, when you look in the popular press about scientific stories in astronomy, you'll from time to time get an article which tries to convince you that there's a diamond sitting in the center of a large planet or star. And this was an example here of an image from I think this was from the BBC website, where the astronomer had obviously talked to the journalist and mentioned the fact that this star would have a large carbon content in the center. And then the journalist went to speak to an artist, and they drew a perfectly cut diamond put in the center of this astrophysical object. Now, this is impossible for many reasons, but one of the reasons that it's impossible from a physical point of view is that diamond is actually a very open structure. The lattice of diamond has a lot of space in it. And if you remember from when I was defining enthalpy, high pressures that you would expect to find in these astrophysical bodies would strongly penalize any extra space in the structure. So it seemed to me that this was a misleading picture. If you talk to the astronomers, they know that these stars don't have diamond. They talk about crystal lattices for their phases. But what we wanted to do is say, well, what actually might be the phase of these very dense forms of carbon? So I worked with a postdoc of mine, Miguel Martinez Canales, when we were at UCL. He's now in Edinburgh. And I managed to convince him to do AIRS, or random structure searches, for carbon at ever-increasing pressures. And it took some persuasion, but eventually he agreed to increase the pressure exponentially, so by orders of magnitude for each new calculation that he did. And in doing this is actually only a section of the phase diagram that we came up with. We actually went up to 1 petapascal, and there are two more thermodynamic phases that we discovered there. So in doing this, we discovered 4 new, potentially thermodynamically stable phases of carbon. BC8 carbon and simple cubic carbon have been known for or theoretically proposed for some time, but we proposed for the first time simple hexagonal face center cubic double HCP and eventually BCC carbon. And intriguingly, this FCC carbon actually was not a close packed phase. It actually was what's known as an electride, where the electrons in the carbon had gone into little pockets, and the structure adopted was actually the calcium fluoride structure, where the fluorines would have been the electrons in this in this system. So a new kind of or a relatively exotic form of bonding was found. Now, when we published this, I mean, largely it was for curiosity. We just wanted to answer the question, what might be the ultimate phases of carbon? But we had some pushback from the referees as to the relevance of this. So it was very pleasing to me that shortly after we published this paper, I was invited to the Lawrence Livermore lab, and there were a group of engineers there who were very interested in phase transitions in carbon. And the reason for that was that the pellets that they're using for laser fusion in the National Ignition Facility were actually often largely carbon-based. And they were very concerned about phase transitions that might happen on the route to laser fusion ignition or inertial confinement ignition. So the basic experiment that's done is you have a pellet of carbon held in the center of a gold can. In the center of that pellet is the fuel, and then you fire many X-ray lasers into the or very high power lasers into the golden can, which then interacts with the gold and then generates X-rays, and those X-rays bathe the outside of the pellet with intense radiation. And then that material starts to ablate off in a spherical way, and you end up with a spherical rocket all heading towards the center of the pellet, and hence high compression. And recently they have managed to have some successes in inertial confinement fusion at the National Ignition Facility. I'm not sure if our phase diagrams helped at all, but they were certainly very concerned about potential phase transitions that might happen in carbon at high pressure. Okay, so towards the end of this talk, I'm now going to turn to novel methodological development. So what are we doing now? So random structure search, there's almost nothing to change. You continue to start your initial random configurations and optimize the structures in some way, but that doesn't mean there aren't things we can do to improve our searching. And one of the things that we've been working with just in the last couple of years is exploiting this revolution in machine learning to accelerate the search. I mentioned that before ab initio random structure searching or first principle structure searching, the pretty much only way that people were doing structure prediction was with empirical potentials. But the problem with those potentials, although they were fast, was that they couldn't handle the entire energy landscapes. However, these new generation of machine learning potentials, which are in many ways very similar to the empirical potentials of the past, is that they're now fitted or trained to a much larger data set. And so there's a hope that they might learn an entire energy landscape, which would allow you then to use it in a brute force algorithm such as random structure search. And so the particular angle I have taken to this is to develop machine learning potentials that are specifically designed for structure search. So I'm not trying to make a ultimate potential that might be put into a library that others might use later on for their projects. I am interested in making bespoke potentials that I can make quickly for the exact search that I'm about to do. And the cartoon shown here is highlighting that of the space of all possible configurations of structures is rather large. But when you're doing a structure search, you're normally operating in subspaces of that region. And so what we're interested in is making potentials quickly and easily that operate in these subspaces. So the basic idea between the potentials that I've derived, now there are a large number of other machine learning potentials on the market, as it were, at the moment, but my interest was on simplicity, ease of training, and robustness. And so the approach I took was based on an observation that we'd made in our group that Lennard-Jones style potentials are actually rather good at identifying different crystal structure, different binary or ternary crystal structure types. So the types of structures can be represented quite straightforwardly with these simple potentials. The relative energies of the phases are not very well described, but the structures can be described. So I looked to develop a potential based on the very simple Lennard-Jones form. Now, Lennard-Jones has a two-body term which describes the interactions between pairs of atoms, and then you have a repulsive term that has 1 over r to the 12 form, and an attractive term that is 1 over r to the 6. Now, this is a two-body contribution to the total energy, and is good maybe for binaries or ternary systems. But if you have an elemental system or a system exhibiting strong covalent bonding, this two-body term is not likely to give you a good description. So I went one step further and I wrote down what I would think Lennard-Jones might have written down to describe a three-body interaction, where I consider the interaction from a central atom to two neighbors, and also between those two neighbors themselves. And essentially what this three-body term is, it's allowing an angle to open up between pairs of bonds. So the K and J here through the M term has a repulsion that pushes those atoms apart, and therefore can form, for example, sp2 hybridization in carbon and so on. So I put together a simple potential form based on this, on what's written down on the right-hand side, and then fed the descriptors that are derived from that, or the environment vectors that you can derive from that, into multiple small neural networks. And this adds some nonlinearity. It allows you to fit more complex data sets. Now, to be explicit, in the case of Lennard-Jones, all the functions are a form 1 over r to some power. Now, I generalize this to an arbitrary function of r raised to some power, and because in the end we want our potentials to be cut off in space, I bring that cutoff into this function right from the very start. So instead of a 1 over r raised to different powers, the function that I raise to different powers is this black line on the right-hand side, which is just a straight line from 2 to RC. So RC is the cutoff radius, and beyond there's no further contribution. And you can see that as you raise that simple function to powers, it looks a little bit like what you might get with a 1 over r term. It's not exactly the same, but it has the same, a similar kind of functional form. And then the other thing that we can do is we can extend the three-body contribution to higher body terms using a similar argument. So you end up with a multi-body potential form, which you train. Now, this is the other thing, because we're using this, I'm not training on curated data sets. I'm training this as part of a structure searching campaign. And when we're doing structure searches, we can only really train the potential on small unit cells, because the reason that we're making a potential is so that we can do more searches on bigger unit cells. So if we could already generate the data and do the searches on the large data sets, we wouldn't need the potential. So we train on small unit cells, and that might seem like a limitation, but actually, compared to other data sets, we insist that the small unit cells are extremely diverse. So we're not training on short molecular dynamics trajectories. We're training on random structures, very much in the spirit of random structure searching. That forces the potential to learn from a small unit cell a very wide range of chemical environments. And then when it comes to the nonlinear fits, we use neural networks. There are other fits you can use, but actually neural networks are extremely powerful. We only train on the total energy of the system. This simplifies the approach, and because we have small diverse unit cells, we're still able to learn effectively what the forces are between the atoms, but only through the energy. We do the training of the neural networks using the Levenberg-Marquardt algorithm, which is extremely fast for modest size and accurate for modest sized neural networks. It doesn't work for very large unit networks because it has essentially a matrix inversion in the number of parameters of the neural network at some stage. So there's a limitation to how large networks you can look at, but we actually only look at very small neural networks, typically only with 1 layer and 5 hidden neurons. And then one of the key features is that we do this multiple times, and we combine the results of multiple neural networks together in a linear combination. So we take the result of one neural network with another neural network with another neural network, all added together with parameters, and we adjust those parameters so as to do minimize an error on a held out validation set but we put a constraint that the parameters that we use are always positive. And that's known as non-negative least squares, and it results in sparsity. If you put that constraint, your parameters are either small and positive or zero. And so the neural networks that develop a zero parameter in front of them can just be thrown away. We don't need them anymore. So it sparsifies the data. Because we have an ensemble or a large number of neural networks, we can look at the standard deviation or the variance of the predictions and use this to make an estimate of the error. Here I've plotted error bars on enthalpy curves, which is nice to see. You don't normally see that with pure DFT results. You can see in this case here, we've trained the potential up to 50 gigapascals, and after that, it doesn't really know what it's doing. And we can see that clearly from the data. But the nice thing about this as well is that we can embed this in an active learning scheme, so we know when we don't know very much about a particular configuration, and we can bias the active learning scheme towards those high deviation parts of the landscape. So our active learning scheme is starting with completely random structures that we calculate the density functional theory energies of. We can add some marker structures. You don't have to, but marker structures are structures that we know that should exist in the energy landscape. And then we go around a loop where we make a potential from those, we make a potential from the data set that we have, do some random structure searching with that potential, and then add that data back into the data set. And it iteratively improves the potential. And so here is an example for lithium iron oxalate. So that's a quaternary system with 4 different species. And what it emphasizes here is that the way that we put the algorithm together, and by this iterative active learning process, the descriptive power of the potential is focused towards the low energy part of the energy landscape. And so you can see that there's a very low error in the low energy part of this landscape here, but we tolerate higher errors at higher energies. And the reason we tolerate that is that very rarely are we actually interested in those very high configurations, but we want the energy landscape to be roughly right at these high energies, so that when we do a random structure search, it moves away from those high energy parts towards lower energy regions. If we hadn't described those higher energy parts of the energy landscape, maybe it could easily get trapped in a very deep local minimum, which would hinder any searching. So one point I want to make here is that, so in my career, I've developed many computational methods, and I would say only a fraction of them do we get round to publishing. And I have a kind of a hard constraint on myself on methods that I would actually put to the general public through publication. And that is, if you're presenting a new computational method, it should really be allowing people to do something that they couldn't do before. So before I introduced these ephemeral data-derived potentials, I wanted to make sure that I could do something with them that I hadn't been able to do before. And rather than looking at other people's and seeing if I could beat other people's structure predictions, I thought it was better to go back to my own early structure predictions on silane, right back to the start of random structure searching, and see what would happen if I did that with this new technology. And well, quite strikingly, and obviously you've seen that I published the paper, we found something new. So at high enough pressures, we found a completely new and very large complex structure with 60 atoms in the privative unit cell, which was beyond conception on the early days of structure prediction, which actually was much more stable from an enthalpy point of view at higher pressures. So this, for me, it convinced me that this approach is it's not just so that we can say we're doing using machine learning. Actually, using machine learning is helping us in these searches. So, kind of some examples of applications of these methods include now allowing us to include temperature in our searches. So this is an example of a phase diagram computed by Pascal Salzbrenner, a PhD in my group, where he was able to develop a potential for lead, including spin orbit, to do calculations, including, now here we got melting lines here, including coexistence melting, that are simply not possible from a first principles point of view. You can't converge these spin orbit metallic calculations to a level of accuracy in large enough unit cells where you can actually run long enough coexistence and molecular dynamics simulations. And also what's incredibly striking for me is these fairly simple potentials are giving essentially quantitative agreement with what's experimentally known about the phase diagram of lead, to the point that we didn't need experiment at any point in these calculations. If we, having never seen a phase diagram of lead, presented our phase diagram of lead, it would agree reasonably well, with some variations in the pressures of the phase transition between FCC and HCP. But not only that, is how fast these calculations are. So this is a table, I mean, one of my favorite tables that Pascal has produced, which shows us just how much faster for searching his new potential was compared to DFT. And so in his table, he has two entries, DFT and EDDP, and his quantity is number of structures per hour per core. And for DFT, it was 0.0004 structures per hour per core. And for EDDPs, it was 37. Now, this is a factor of about 100,000 different, which is completely transformative. So indeed, it's a very exciting time, I think, in materials modeling at the moment, with the advent of these machine learning potentials that many groups are contributing to and exploring the possibilities of. I feel like a door has been opened and we're able to do things that we just couldn't before. So it's not just a case of doing things faster that we were doing before. It's actually enabling completely different things to be done. And I'm going to give an example of this here by reflecting back on effectively what is an AIRS or an ab initio random structure search. So in an ab initio random structure search, we build a unit cell, we feed it into a code like CASDET, and we relax the structures to the nearest lowest energy, and then we store the result. And this is the optimization that we do. Now, because we have these possibly hundreds of thousands of times faster potentials, we can do things we wouldn't have dreamt of doing before. So now we've been introducing the idea of what's known as hot AIRS, where instead of just relaxing the structure, we do the same thing. We build a structure, we relax it, and then we can do a long, possibly half a nanosecond or multiple picosecond anneal at a given temperature, and then we relax the structure again and store it. Now, from the point of view of random structure search, the results that we output are relaxed structures. And this is in some ways just thought of as a more complicated optimization algorithm, but it's physically motivated, especially as now in a metallurgy department, I can see the importance of annealing. In some ways, it makes random structure search a bit more like a simulated annealing. Okay, but it's not exactly the same as simulated annealing. It's kind of the same as doing lots and lots of independent molecular dynamics simulations. But the difference is in the quantity. Now we're doing maybe thousands or tens of thousands of molecular dynamics simulations all at once. And the powerful thing that allows us to do is we can now do structural searches using thousands and thousands of molecular dynamics simulations, and you see a very different picture. So what I'm showing here is a structure search done with 256 silicon atoms in a cubic periodic unit cell with the density close to the diamond structure. And the red curve is normal AIRS. So this actually emphasizes the limitations of random structure searching in very large unit cells. In a big enough unit cell, you start to mostly only explore the random melt-like or amorphous-like structures. They have the highest entropy. They take up the largest region of configuration space. And you have a very low probability of finding more ordered, lower energy structures. But now if we do an anneal, in this case, 900 Kelvin for 500 picoseconds, many thousands of times, we can actually get a density of states of annealed structures. And interestingly, we see remnants of the quenched melt peak. We also see a separate peak, which looks like clearly amorphous phases. But then at low energies, we see yet another peak, which are the crystalline phases, or in fact, polycrystalline, because in this shaped unit cell, there's no single phase crystal that would fit in. And this for me is quite exciting. It allows us to access a much larger range of structure, a much larger unit cell structures for random structure search, but also, of course, allows us to explore the amorphous state or the disordered state or microstructure in complex materials. Okay, so I'm going to finish now. I think it's coming up to the end of the allotted time. I have many people I want to thank, particularly Richard Needs and my whole list of collaborators over years, and there are my funders on the right-hand side. As mentioned at the very beginning, my AIRS codes and my EDDP packages, they're all open source. You can go to the website and just download them and play with them. If you're interested and have questions, feel free to email the team, which is largely me, at the email given at the bottom right-hand side. And I thank you very much for your attention.